In this video, we introduce graphs. Now imagine that an organization wants to set up teams of 3 to work on some projects. In order to maximize the number of people on each team who had previous experience working together successfully, the director asked the members to provide names of their previous partners. This information is provided on the following slide, so right here. So here we have a table of everyone and who they've previously worked with. Now what we can do is we can use this table to form a diagram that connects everyone who has previously been partners. Such a diagram could look like this. Right? So anyone connected by a line has worked together. Drawings such as this here are illustrations of a structure that's known as a graph. So the dots are called the vertices, which is the plural of vertex, and the line segments joining the vertices are called edges. Now from here, we can see that it is possible for edges to cross at points that are not vertices. Right? For instance, right here, we have 2 edges crossing, but that is not a vertex. Now also note that this type of graph is different from the graph of a function. For this reason, we often refer to graphs of functions as plots of the function. This is to avoid confusion. And everything I just said is summarized on this slide. Now note that edges need not be straight. They can also be curved and must either connect one vertex to another vertex or to itself, right? A loop. So here we have another graph. Now in this graph, we can see that the vertices are labeled with V's and all the edges are labeled with E's, right? Here's a vertex, 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 vertex. Right? So there's 7 total vertices, and we have 6 total edges. Right? Look, notice here, right? Edge 2 is not straight, it is curved. Edge 3 is not straight, it is curved. And right here, edge 5 is a loop. But look that every edge is connecting 2 vertices. Now, we say, right, E2, E3 we call parallel edges. E5 is a loop, and V5 is called an isolated vertex since there are no edges that are connected to it. Now, these 2 edges are said to be parallel even though they intersect at the vertices. So we provide formal definitions now. A graph G consists of 2 finite sets. A non-empty set of vertices, which is typically denoted as V of G, and a set of edges, typically denoted E of G, where each edge is associated with a set consisting of either 1 or 2 vertices, called its endpoints. The correspondence from edges to endpoints is called the edge-endpoint function. An edge with just one endpoint is called a loop, and 2 or more distinct edges with the same set of endpoints are said to be parallel. An edge is said to connect its endpoint, And two vertices that are connected by an edge are called adjacent. A vertex that is an endpoint of a loop is said to be adjacent to itself. An edge is said to be incident on each of its endpoints. And two edges incident on the same endpoints are called adjacent. A vertex on which no edges are incident is called isolated. Now, this next definition we've actually worked with before, we just never actually formally defined it, and we do so now. A directed graph, or a digraph, consists of two finite sets, a non-empty set of vertices and a set of directed edges, where each is associated with an ordered pair of vertices called its endpoints. If edge E is associated with the pair VW of vertices, then E is said to be the directed edge from V to W. We did directed graphs when we looked at relations. Now, let G be a graph and V a vertex of G. The degree of V, which is denoted degree of V, equals the number of edges that are incident on V, with an edge that is a loop counted twice. So let's practice finding degrees on this graph. So we want to find the degree of each vertex. So we start with the degree of V naught. So I'm sorry, not V naught. V1. It's our first vertex. Well, notice there are no edges incident on it, so it has no degree. All right, let's now look at degree of V2. So we have edge 1 is incident, edge 2 is incident. That gives us 2. And finally, degree of V3. Edge 1 is incident, edge 2 is incident, and edge 3 is a loop, so that counts twice. So that degree is 4. Now, the subject of graph theory began in the year 1736 when the great mathematician Leonhard Euler published a paper giving the solution to the following puzzle. The town of Königsberg in Prussia, which is now Kaliningrad in Russia, was built at a point where two branches of the Pregol River came together. It consisted of an island and some land along the riverbanks. These were connected by 7 bridges. Is it possible for a person to take a walk around town, starting and ending at the same location, and crossing each of the 7 bridges exactly once? So here we have a map of town, and for this problem, we can simplify it to this map right here. Right now, notice this whole thing is landmass A, this is landmass B, landmass C, and landmass D. It should be apparent that you can get to any point from any point in one landmass without crossing any bridges, right? So you can totally traverse landmass B without crossing a bridge, C, D, so on, right? So the solution to this problem can be found by converting it to a graph theory problem. And I just mentioned this. Each landmass can be completely traversed without the use of a bridge, so we can treat each landmass as a vertex and each bridge as an edge, as shown here. problem now becomes, is it possible to find a route through the graph that starts and ends at the same vertex and traverses each edge exactly once? Or equivalently, is it possible to trace this entire graph, starting and ending at the same point, without ever lifting your pencil from the paper or crossing an edge more than once? Answer is no, and the reasoning will be left as an exercise. So this introduces some new terminology that we should introduce. So let G be a graph, let V and W be vertices in G. A walk from V to W is a finite alternating sequence of adjacent vertices and edges of G. Thus, a walk will have the form V0 E1, V1 E2, so on and so forth, where the V's represent vertices, the E's represent edges. V0 is V, Vn is W, and for each of the I's, Vi minus 1 and Vi are the endpoints of the edge EI. The trivial walk from V to V consists of the single vertex V. A trail from V to W is a walk that does not contain a repeated edge. A path from V to W is a trail that does not contain a repeated vertex. A closed walk that starts and ends at the same, a closed walk is a walk that starts and ends at the same vertex. A circuit is a closed walk that contains at least one edge and does not contain a repeated edge. And a simple circuit is a circuit that does not have any other repeated vertex except the first and last. So that is summarized in this table. So here we're going to be given a graph and several walks, and we're to determine whether they are trails, paths, circuits, or simple circuits. So let's start with A. Alright, so V1, V3, V3, V4. This does have a repeated vertex, namely V3, but it does not have a repeated edge, right? E1, E3, E4, E5. Thus, it is a trail from V1 to V4. If we now look at part B, right, so let's actually write this out. So A is a trail. If we look at part B now, it's just giving edges, so V1 to V2, then we use E3, so that goes up to V3. E5 goes to V4, we go back to V3, and then E6 to V5. So it has this repeated edge of E5, which means it has a repeated vertex of V3. So this is none of them. This is just a walk. If we look at C, we go from V2 to V3. That requires us to use edge 3. Then to V4, that requires us to use edge 5. Then to V5, which requires us to use edge 10. Back to 3 requires us to use edge 6. To V6 requires us to use edge 7. Back to V2 requires us to use edge 8. So it starts and ends at V2. It contains 6 distinct edges. So this is a circuit. But since V3 is being repeated, it is not simple. So this is just a circuit. Look at D. You go V2 to V3 to V4 to V5 to V6 back to V2. So this starts and ends at V2. And it has 5 edges. We went V2 to V3, over to V4, down to V5, over to V6, back to V2. None of the edges were repeated. None of the vertices are being repeated except for V2. So not only is it a circuit, this is a simple circuit. E, V1 to V2 using edge 1, then using edge 1 back to V1. So we go from here to here to here. So we have the walk starting and stopping at the same vertex, and it has a repeated edge. So this is just a closed walk. And finally, F is just the trivial walk. It's the single vertex. Notice by definition, a trivial walk also defines a trail. Because remember, a trail did not have repeated edges, could have a repeated vertex, has to start and end at the same point, and does not have to contain at least one edge. So trivial walk, which is also a trail. A graph H is said to be a subgraph of a graph G if and only if every vertex in H is also a vertex in G, every edge in H is also an edge in G, and every edge in H has the same endpoints as it has in G. Notice this is very similar to the definition of a subset. Right, so basically, H is a subgraph of G if V of H, the set of vertices in H, is a subset of the set of vertices in G, right? That's what it means for every vertex in H to be a vertex in G. And every edge in H, so the set of edges is a sub in H is a subset of the set of edges in G. Furthermore, every edge in H has to have the same endpoints as it is in G. So the edge endpoint functions must be equal. Here we're asked to list all subgraphs of the graph G, where the vertices are V1 and V2, and the edges are E1, E2, E3, and the endpoints of E1 are V1 and V2, the endpoints of E2 are V1 and V2, and E3 is a loop at V1. So let's actually try and draw this graph out. So we have two vertices, V1 and V2. Let's call that V1 up there. Let's call this V2 down here. We're going to have three edges. So the endpoints of E1 are V1 and V2. Endpoints of E2 are also V1 and V2. And E3 is a loop at V1. So our graph could look something like this. We want all possible subgraphs. Well, there are three really easy subgraphs. The subgraph that only has vertex 1, the sub that only has vertex 2, and the subgraph that has both vertices but no edges. Now let's look at starting to add edges. So we can do this. That contains both vertices and only edge 1. Alternatively, we could do this. Contains both vertices but only edge 2. We could do this. Only has the first vertex, but it has the third edge. We could also do where it has V1, E3, and V2 but no other edges. We could then do where it has both vertices and both E1 and E2. It has both vertices and it has E1 and E3. Has both vertices. Has E2 and E3. And then, of course, the graph itself. So this gives us, should be a total of 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11 of them. Intuitively, a graph is connected if it is possible to travel from any vertex to any other vertex along a sequence of adjacent edges of the graph. We formally define this here. Let G be a graph. Two vertices V and W are connected if and only if there is a walk from V to W. The graph is connected if and only if any two vertices VW are in the set of vertices of G. There's a walk from V to W. So here we're asked to determine which of the following graphs are connected. Okay, well, let's see. A is clearly connected, right? No matter what vertex we start at, we can easily get to any other vertex. B is obviously not connected. Obviously, if we start at V4, we can't get to any other vertex. Now C. C is also not connected. And here's why. These edges are intersecting at non-vertices, so we could just as easily draw it this way. Excuse me for a minute. Okay, that worked. I don't know what was going on there, but it's working now. We can just as easily draw C this way. Here's V2, V6. Here is V3, V5. And here is V1 and V4. Drawn this way, it is now completely obvious that we cannot get from V1 to like V2, let's say. So C is also not connected. So the only one that is connected is A. Now let G be a graph. If G is connected, then any two distinct vertices of G can be connected by a path. If vertices V and W are part of a circuit in G, and one edge is removed from the circuit, then there still exists a trail from V to W in G. And finally, if G is connected and contains a circuit, then an edge of the circuit can be removed without disconnecting G. A graph H is called a connected component of a graph G if and only if three conditions are satisfied. First, H is a subgraph of G. 2, H is connected. And 3, no connected subgraph of G has H as a subgraph and contains vertices or edges that are not in H. Here we're asked to find all the connected components of the graph shown. Well, there's going to be 3 of them. H1 can be described. V1 is the set of vertices V1, V2, V3, along with the set of edges E1, E2. So this is a connected component right here. We have H2, which can be described as a set of vertices that contains V4, and the set of edges, which is empty, so it has no edges, right? That is this component right here. Then finally we have H3, which can be described. V3 is the set of vertices, V5, V6, V7, and V8. And the set of edges, E3, E4, and E5. Right, so that is this component right here. And that will conclude our video on graphs.